Swayam Prabha. Digital India. Educated India.
Now we know for this the determinant is, we can verify it using the standard ideas, determinant of A equal to 0. Now geometrically what is happening over here? We know that this was my original thing, and after transforming I got what? This vector became the vector 2, 2. The second, this vector also became the vector 1, 1. Right? Now what has happened? I had two independent vectors over here. After transforming, I got a set of what are these vectors? They are dependent vectors. Right? And what is, if I ask you the same thing, what is are these 2 points over here? What is the area of the so-called parallelogram formed by these two vectors after transformation? 0. I mean, it is not forming a full-fledged two-dimensional object. It's basically forming only in one-dimensional object in this case. Area of that turns out to be 0. So when the determinant is 0, the matrix is singular. What that also means is, and what do we know, what are the columns of these matrices? The columns of these matrices are basically vectors after transforming. So determinant of the matrix is 0. It means in the transformed space, these vectors have become dependent. Or these vectors have, instead of lying, you started with started with two independent vectors over here. In 2 dimensions you got 2 dependent vectors. In 3 dimensions it's possible that you started with 3 independent vectors, and after transforming it's possible that all the 3 vectors are lying on the same straight line, or it is possible in 3 dimensions that 2 of them are lying on one plane, or they are lying on one plane. So after transforming you have these 3 vectors over here. After transforming, all the 3 vectors are lying on one plane, and therefore instead of forming a full 3-dimensional parallelepiped, the area of this it forms only a 2-dimensional figure, and therefore the volume of that figure is 0 and the determinant is 0. So that's why when a matrix is singular, it means the columns of these matrix are dependent on each other. And you can go back and see, right? If you go back to rules of expansion of how determinants are expanded, if one column can be written as a combination of the other columns using a standard expansion for volume of determinant will be 0. Likewise, conversely, if determinant is 0, it means one column can be written as a linear combination of the other columns, or the columns are dependent. Or you started off with 3 independent or n independent basis vectors. After transforming, they no longer remain dependent if the matrix is singular or determinant is 0. If the determinant is non-zero, the vectors after transforming, they continue to remain independent. Okay, so we'll try to see how all of this is helping us to solve linear equations, because that's how I said I motivated this talk from. So let's take two equations in a plane. So x plus y equal to 1 and 2x plus y equal to 2. This is very standard interpretation which all of us have seen right from high school, which is, if I ask you, again as I said, this is the algebraic. I give you 2 linear equations, you know how to solve them algebraically by using various elimination formulae, you can do that. Geometrically we have seen this interpretation also. The first equation is basically a line in this plane. Right? This is the first equation, is representing a line in this plane. This is x plus y equal to 1. The other equation is representing another straight line in this plane. So this is 2x plus y equal to 2. So now the typical interpretation that you are asking, when each equation represents a line in 2 dimensions, in 3 dimensions an equation will represent a plane. In higher dimensions, something again we cannot visualize, each equation represents what's called a hyperplane. Now this typical standard picture that we have of solving linear equations is, in 2 dimensions each equation represents a line. So we are asking, do these lines intersect? And if these lines intersect, do they intersect at a point, or does it have multiple solutions? In this case we know that these are non-parallel lines, therefore they intersect non-parallel lines intersect uniquely at a point, and this is a solution. Solution is 1, 0. right? Yeah, 1 comma 0. This is very standard row interpretation that we have seen right from high school. I can also give you what's called the column interpretation, and all of this is that is, let me clean out everything. Yeah. So I can write on my right hand side, I have this vector 1, 2. We know what it represents. It represents some point in 2 dimensions, and I am going to write this as this is the column picture or the column interpretation system of linear equations. Now, what is my right hand side? Right hand side is some vector x 1, 2, and what is my left hand side? Is a linear combination of 2 vectors. The 2 vectors being the first vector over here 1, 2, and the second vector over here being 1, 1. So the question in terms of the row interpretation I was asking was, each row represents a line. Do these lines intersect? If they intersect, do they intersect uniquely in a point, or do they have multiple points of intersection? That was a question that I was asking in 2 dimensions. In 3 dimensions, as far as row picture is concerned. Now the column picture is, I represent the right hand side as a column, and each of these I represent as a column vector over here, and asking you, so what is the question that I am asking you? Is there a linear combination of these 2 vectors which gives me the third vector over here? Can you find a linear combination of these 2 vectors which gives me the third vector over here? So in this case, the answer, in the case of the row vector, in the row picture, it was that, do these lines intersect, and if they intersect, do they intersect uniquely at a point, or do they intersect at multiple points? The column picture is there a linear combination of these column vectors which gives me my right hand side vector, the vector 1, 2. And what is the answer in this case? We know from the row picture it had a solution. The solution was a point x equal to 1, y equal to 0, so that was a solution. So here also we know there is a solution. The solution is the same. Solution has to be the same because mathematically you are solving for the same unknowns x and y, except the interpretation is different. In the first case, I was talking about taking each row and representing it as a line. In the second case, I am taking linear combination of columns of the matrix. So if I want to represent the matrix as A as 1, 1 and 2, 1, in the first interpretation I was taking rows, lines which are being formed from the rows of A, and now I am taking vectors which are being formed from the columns of A. And I am asking you, is there a linear combination of the columns of A which gives rise to the right hand side vector over here 1, 2? And I know that exists because these vectors are independent, and therefore I can always find a solution. We know that these 2 vectors are independent. They are pointing in 2 different directions in the plane, and we know they are independent. Therefore, you can always find a linear combination of these vectors which gives me this vector over here. So this was a case, it was a simple enough case where all the solution, or that was a unique solution. Now what happens when x plus y equal to 1 and 2x plus 2y equal to 2? So the row picture is what? They are basically getting, both of them are really the same line. I have given you 2 equations, but they are really the same because the second equation is just a multiple of the first equation, and geometrically each row, as I said, represents one line, and in this case both of them are representing the same straight line. So how many solutions do they, how many points do they intersect in? Infinite points, because all the points on these lines are basically points of intersection of these 2 lines. So there are infinite solutions in this case. Right? Column picture, what happens? I am asking you this solution, this question. In this case, both of these are the same thing. Both of these 2 vectors happen to be the same. So I am asking you, the 2 vectors, the 2 column vectors are the same. So I am asking, is there a linear combination of these 2 vectors which gives me the same vector? Yes. There are, how many such cases are there? There are infinite cases, right? I could take x equal to 0, I'll get y equal to 1, I could take y equal to 0, I could get x equal to 1, and I could take, obviously, other combinations are also possible. I could fix x is equal to minus 1. What would y be? 2. So there are infinite such solutions over here. So there are infinite linear combinations of these 2 vectors. In this case, it happens to be unfortunately the same vector. There are infinite combinations of this which gives me my right hand side vector. So in both the cases, the row interpretation or the column interpretation, the final answer is the same, that there are infinite solutions. However, the interpretation is different. In the first case, it was, are these lines happen to be parallel and collinear or the same. In the second case, basically I had these two vectors were independent, and I was asking you whether the right hand side vector could be written as a combination of these two dependent vectors, and it could be written. There are infinite such solutions. However, why does this happen over here? In the previous case, why did we get a unique solution? In this case, why did we get multiple solutions? In the previous case, the vectors were independent, or the matrix had a non-zero determinant. In this case, the matrix, if I want to look at this matrix over here, 1, 1, 2, 2, the matrix of these two vectors over here, they were dependent. It was the matrix was singular, determinant was 0. So I am only trying to give you a very rough geometric intuition using 2 dimensions. In 3 dimensions, it slightly gets more complicated, but we will just try to generalize this to higher dimensions. So when the determinant is non-zero, as in the previous case, the vectors were independent. We know that for a square matrix, when the vectors are all independent, they are pointing in some sense. When the vectors are independent, determinant is non-zero. You can always write a right hand side vector as a linear combination of these vectors, and therefore there was a unique, and we know that there is always a unique solution. When the matrix, however, became singular, the vectors after transforming became linearly dependent. We found in this particular case infinite solutions. However, that is not the only case which is possible. So let me take x plus y equal to 1. What do they represent? They represent parallel non-intersecting lines. Obviously, there is no solution at all. And the column picture is the same. I mean, I am asking you the vector. I can take this vector, in this case happens to be the same, 1, 2, x times this vector plus y times again this vector over here. Can it ever give me a vector 1, 3 which is away, so 1, 2 is this. So all linear combinations of these vectors are going to lie only on this line over here. Can I ever get a vector 1, 3 which does not lie on this? No matter what kind of linear combinations, like positive, negative, infinite, infinitely small values for x, large values for x, I can never, if I take linear combinations of this vector, I will always be lying only on this line. I will never be able to get even 1 micron or 1 nanometer or 1 femtometer out of this line. So no matter what combinations I take, I can never get out of this line. So I don't ever have a solution for this case over here. So when these two vectors, in the case when the matrix, determinant of the matrix happens to be 0, I could have two cases, in multiple solutions or infinite solutions, or the other case is no solution at all. So what it means geometrically is, let me erase all of these two things. In 3 dimensions, it's what it means is, each equation represents a plane, and I am asking you, are these equations, are these planes intersecting at a point? If the planes are intersecting at a point, you get a unique solution. Now, however, they may intersect not just it is possible that so 2 of these planes are parallel, and the third plane is not possibly parallel, but 2 planes are parallel, then you will never be able to get a point of intersection. So you may not get a solution. In the column picture, what could happen is, two of these equations are lying in one plane, and the third the right hand side vector, three vectors are lying in one plane, and the right hand side vector is not lying in this plane. So I am asking you, x times this vector plus y times this vector plus z times this vector. So let us this plane over here, and my right hand side vector is not lying in this plane. No matter what linear combinations I take, I will never be able to get the solution. So that is the column picture. I will not be able to find linear combinations of these given vectors, which gives me my right hand side vector, and therefore there exists no solution in this case, and that's because the determinant was 0. If fortunately the right hand side vector lay in the same plane, then there are infinite solutions. This is in 3 dimensions. So now how do we generalize this to higher dimensions? We need to define certain properties for a matrix called a rank of a matrix. Now a matrix is as I said, there are m rows and n columns. Now, the number of linearly independent rows is called the row rank of a matrix. So, obviously, the row rank is smaller, cannot be larger than larger than m. Likewise, the column rank, that is when I say, what I mean by it is, I mean writing vectors as columns, but I could also take a row vector and then treat them as vectors. That is largely a stylistic reason why vectors are usually denoted in books, for instance, as column vectors, but vectors for all practical purposes could also have been denoted as rows. Right? In this case, I take this as a vector and I can ask you how many of these vectors are dependent and how many vectors are independent. The number of linearly independent rows is called the row rank. The number of linearly independent columns is called the column rank. So, column rank is small, cannot be larger than n, the number of columns. There are n columns and m rows. Now, there is a very fascinating fact in linear algebra. It says that row rank is equal to column rank. So, think about this. If I give you, what this means is, if I give you a 1000 by 2 matrix, obviously row rank is equal to column rank. Row rank cannot be larger than 1000. The column rank cannot be larger than 2. What this means is, only at the most only 2 of these rows can be independent. That is also not guaranteed that all the two rows are independent. Even though there are 1000 rows, only 2 of them are independent. That also makes sense, right? Because 1000 rows would mean 1000 vectors, and we know that in each of these is vector of size 2, and we know that in the 2 dimensions only 2 vectors can be linearly independent at the most. You cannot have 3 linearly independent vectors in 2 dimensions. So, even though you may have a 1000 by 2 vector matrix, only 2 rows could be independent. All the other rows could be written as linear combinations of these rows. Likewise, if it were a 2 by 1000 matrix, this is 2 and this is 1000. At the most 2 columns are independent. All other columns can be written as linear combinations of these. This also makes sense because in a plane we know that there are only 2, at the most 2 independent vectors, and any other vector can be written as combinations of the 2 independent vectors. So, at the most there can only be 2 independent columns. So, the rank of a matrix, the surprising fact, as I said, and it can prove it, which you won't do this, is the row rank equal to the column rank, which means the number of, if the row rank were 1 in this case, that also means if I had a 2 by 1000 matrix and the row rank was 1, that also means there is only one linearly independent column. Likewise, if this were for this matrix, if the column rank was 1, which means there is only one linearly independent column, it automatically means there is only one linearly independent row. All other rows are combinations of these. So, row rank equal to column rank. So, for a matrix, a rank is uniquely defined as the number of either linearly independent rows or the number of linearly independent columns, and it is uniquely defined. So, now let us try to ask this question in a large number of sense. So, Ax equal to 0. So, A is of size n cross n, x is of size n cross 1, and the right hand side is a vector, it is a vector of size n cross 1. Right. So, now I am asking you this question, Ax equal to 0, does this have a solution? It always has a solution. I am only interested in square systems of equations now. Then later on we will look at underdetermined and overdetermined equations, which means more number of variables or less number of variables. Those we will come to later. Right now we are only interested in square systems of equations, which means as many equations as there are variables. So, Ax equal to 0 always has a solution. And what is that? This trivial solution, x equal to 0. When I say x is a vector of n independent x is a vector x1, x2 all the way up till xn. This equal to 0 is always a solution for this. If there exists a non-trivial solution, which means at least one of these elements is non-zero, what does it mean? It means that the columns of A are dependent of dependent. And how do we see that? See, I can write this matrix A as A1, A2, An, where each of this is a column vector. Matrix is of size n cross n. I write the matrix A as series of columns. A1, A2 are all column vectors. Each of them is a size n cross 1. Now, if what this means is x1, x2, xn is equal to 0. So, I am asking you this question, x1, a1 plus x2, a2 and x dot 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 xn, an equal to 0. If there exists a non-trivial solution, non-trivial means at least one of them is non-zero, then obviously the vectors are all dependent, the column vectors are all dependent. So therefore, if there exists a non-trivial solution, the column vectors are dependent. Conversely, if the column vectors are dependent, then there exists a non-trivial solution. So if the column vectors are dependent and there exists a non-trivial solution, what can you tell me about the rank of A? The rank of A cannot be equal to n, because some either some row vector or column vectors are dependent on each other. In this case, column rank is also smaller. So the column rank is smaller than n. It means some column vectors are dependent on each other. Therefore, some column vectors are dependent on each other. There exist non-trivial solutions. The determinant of that matrix also happens to be 0. So there is a non-trivial solution. For it to exist, both cases, the equal implication holds in both directions. If determinant of A equal to 0, then there exist non-trivial solutions. Conversely, if there exist non-trivial solutions, it means the columns are dependent, and we know what happens when columns are dependent, the determinant is equal to 0. Now, what happens in the case, again I am talking about only square systems, Ax equal to b. It has a solution for in this case my right hand side need not be 0. The difference between the previous case and this is, the previous case right hand side was 0, which means that always sags the solution, the 0 solution was always there. However, in this case, as we saw by a couple of examples, it is possible that there may not exist a solution. In the case when for instance, when there were two non-intersecting parallel lines or two non-intersecting parallel planes and so on, it is possible that there may not exist a solution. So when you ask about in the general case, when A is of size again x is n cross 1, I am asking you this question: when does that exist a solution? Obviously, if you look at the column picture, I am asking you, is there a linear combination of the columns of A which gives me my right hand side? Now, if my right hand side were in such a manner that it was not possible to write these as combination of columns of A, which would mean that that vector is sticking somewhere else. So that means I get one more independent vector. If it cannot be written as a combination of columns of this, which means a vector, if I take all the column vectors of A and the column vector B and I stack them together, if I want to be able to find a solution, then this matrix, the rank of this matrix has to be equal to the rank of the original matrix A. Why? Because I should be able to write B as a linear combination of the columns of A, which means whatever the number of independent columns are there in A, the same number of independent columns should be there in the so-called augmented matrix, which has columns of A and B. If by adding columns, I cannot decrease the rank, I can possibly increase the rank. But if the rank increases, what that means is the vector B cannot be written as a linear combination of the columns of A, which means I cannot find a solution. So the solution exists if and only if the rank of A is equal to the rank of the so-called augmented matrix, where you have A and B. This is a matrix of size n cross n plus 1. If the rank of this matrix becomes larger than the original rank of the matrix A, I will not find a solution. Why? Because then the right hand side vector is not possible. It is not possible to write it as a linear combination of the columns of A. It is not dependent on these columns of A. Therefore, I get one more independent vector. I get the rank is increased by 1. Therefore, I could not have a solution. Now, if I did not say what the rank of this matrix was, it could be n, it could be smaller than n. If the rank is smaller than n, but after augmenting it, if the rank is the same as the original matrix, then it has a solution. Now, suppose it happens that the columns of the rank of the original matrix is n. The columns are independent, then there always exists a solution, because I can always find a linear combination of the columns which gives me my right hand side. If the columns are independent, then there always exists a solution, and more importantly, the solution is unique. If the columns are independent, that is, or the rank of the matrix A is n, then there exists a solution and it is unique. If the rank of the matrix A is equal to rank of the augmented matrix AB, and this is smaller than n, then what it means is the right hand side vector B can be indeed represented as a linear combination of the columns of A, and there exists infinite such solutions. Not just one solution, but there exists infinite solutions. If the rank of the augmented matrix is larger than the rank of the original matrix, obviously there exists no solution. These can also be viewed in terms of the determinant, as we discussed. If determinant is equal to 0, the solution may or may not exist. If determinant of Ax equal to 0, b, I can also view this in terms of determinant. I can ask this question, is determinant equal to 0? Yes, no. If determinant is not equal to 0, unique solution. If determinant is equal to 0, then there may or may not exist a solution. And if there exists solution determinant of A is equal to 0, then there are infinite solutions. So let me just recap. For Ax equal to b, a square system of equations, if determinant of A is not equal to 0, then solution exists and it is unique. If determinant of A is equal to 0, then there may or may not exist a solution. If there exists at least one solution, then there exist infinite solutions.